Electropotentials and electrochemical cells. So what is the purpose of an electrochemical cell? Well, they actually act as batteries, and that's because they convert chemical energy into electrical energy. Now, in terms of how they actually work, in essence, they're comprised of two metals. Crucially, they need to have differing reactivities. And what that does is it sets up a redox reaction. And as we know, with redox reactions, reduction and oxidation take place, which by definition means that there's a transfer of electrons. So that's in essence how these electrochemical cells work. So here's a simple diagram of an electrochemical half cell. We have a metal bar being dipped in a solution of its own ions. This means that an equilibrium is set up, and we call this arrangement an electrode or a half cell. So there's our metal bar, in this case it's solid iron. Here's our electrolyte containing positive ions of the same metal, in this case Fe2+ ions. In its simplest form, an electrochemical cell is comprised of two half cells which are connected by a wire and a salt bridge. So here's a diagram taken from my revision guide, which is available to purchase at swhlearning.co.uk. I'm super proud of these guides. They are crammed full of perfect exam wording and explanations. So in its simplest form, an electrochemical cell comprises of two half cells. There's the wire we mentioned and the salt bridge. In this case, we have two metals, iron and copper. They have differing reactivities. Remember, iron is more reactive than copper, so that's going to set up a redox reaction. They often like to ask you what the purpose of the salt bridge is. The purpose of the salt bridge is that it allows ions in the ionic substance to flow. So in essence, the salt bridge exists to complete the circuit. If you're interested, the salt bridge tends to be made from potassium nitrate. The key thing here about the salt bridge is that the ions used must not react with either electrolyte, and that's something that commonly gets asked. If you have a look up here, you've got a voltmeter that's added to the circuit in order to measure the electromotive force, the EMF, in volts. If you're keen for your cell reaction to go to completion, it's very important that the voltmeter is removed from the circuit. You often notice that the electromotive force is given this symbol, E theta, and it's not possible to measure the EMF of an electrode on its own. It must be measured between two connected electrodes, as we see here. Now, the EMF of all electrodes is measured by connecting them to a standard hydrogen electrode. That standard hydrogen electrode is given an E theta value, so an EMF of 0 volts by definition. Let's take a closer look at the standard hydrogen electrode. They often ask you the components of a standard hydrogen electrode. So the first thing to mention is that it involves hydrogen gas at a pressure of 100 kPa. You have a concentration of 1 mole per dm cubed hydrogen ions, HCl. You've got a temperature of 298 Kelvin, and you have the presence of a platinum electrode. So those are your components of a standard hydrogen electrode. It's also important that the concentrations of the ions in solution of the attached half cell, which we see here, should also have a concentration of 1 mole per dm cubed. As I've already mentioned, by definition, the electrode potential of the standard hydrogen electrode is 0 volts, and that allows the E theta value of all other electrodes to be measured as a comparison. Now we're going to discuss the conventional representation of half cells. So I'll write out an example here of a half cell. There's your platinum electrode. The first thing I want to point out is that a solid vertical line indicates a phase boundary, e.g. between a solid and solution. Your double vertical line here represents a salt bridge. Now your more positive half cell, that means where the reduction reaction is taking place, is always written on the right hand side. I promise I'll explain what that means very shortly. The species with the highest oxidation state in each half cell is written next to the salt bridge. So here's our copper. So we know that reduction is occurring over here. Just compare these oxidation states. C2 plus has a 2 plus oxidation state versus 0 here for copper, which explains why it's nestling up against the salt bridge. Now let's have a look at this side. At the standard hydrogen electrode, this hydrogen here has a 0 oxidation state. This is +1, hence why it nestles up against the salt bridge here. And then the EMF produced should be indicated, although it's not necessarily required by mark schemes. I'm just going to write it here, E theta equals plus 0.34 volts. Now the overall E theta value refers to the difference in the E theta values between the two half cells. So by connecting different half cells to a standard hydrogen electrode, it allows us to develop an electrochemical series. So let's have a look at this table and really work out what it's explaining to us. Now one thing to be aware of is, look, if you have the positive ion, obviously that needs to gain electrons in order to become neutral, so that's where reduction is occurring. If you look at these arrows, you can find that the weakest oxidizing agent, so the species least likely to be reduced to gain those electrons, has the most negative E theta value. So in this case, this lithium ion is the least likely to be reduced. It is the weakest oxidizing agent. Down here at Ce4 plus with the most positive E theta value, that's going to be your strongest oxidizing agent. So those Ce4 plus ions are the most likely to gain electrons. If we consider the right-hand side of the equation, notice that this table shows reduction half equations. Now, the element in its neutral state, these species will obviously therefore lose electrons. They'll be oxidized. So in this case, lithium here is the strongest reducing agent. It's the most likely to be oxidized, to lose electrons. Down here, Ce3 plus is the weakest reducing agent. It's the least likely to lose its electrons. So in the exam, you might find it helpful when you get this table of electrode potentials to actually add these arrows with the labels, but do be careful. Sometimes the exams will list the reactions in reverse numerical order or back to front. So make sure that you're looking out for that. But when written conventionally, the oxidizing agents are the species on the left, as we know, as I was just saying. Reducing agents are the species on the right. The reduction reaction will be carried out by the half cell with the most positive E theta value. This occurs at the positive electrode, which is the right-hand side when drawn conventionally. The reaction occurs as it's shown in the electrochemical series. So yeah, your reduction reaction will just be one of these equations pulled out, whereas the oxidation reaction will be carried out by the half cell with the most negative E theta value. This occurs at the negative electrode, so the left-hand side when drawn conventionally, and therefore we need to write our reaction in reverse in order to show the loss of electrons. And then the E theta cell value overall is calculated using E theta cell equals the E theta value of the reduction reaction minus the E theta value of the oxidation reaction. I personally prefer just learning this, that the E theta cell is your most positive E theta value minus your most negative E theta value. So let's jump in with an example. So we're being asked to consider the following cell diagram and half cell reactions. So what we're actually going to do here is we are going to work out which of these equations represents reduction, which one represents oxidation. We're then going to rewrite those equations, making sure we flip the oxidation equation. We'll balance the electrons, and then we'll finally combine the equations to give the overall reaction of the cell before finding the total E theta of the cell. So I've pulled down the rules that I just went through so you can actually see how we're approaching this question. So first of all, we need to identify which reaction is reduction. We're looking at the most positive E theta value, which is this number here. So we're going to label that reduction. This reaction is oxidation. Now the reduction reaction we write left to right. So I'm going to keep that Ni2 plus 2E minus producing Ni solid. Just label that E theta value. It says here that for the oxidation reaction, the reaction needs to be written in reverse. So I just need to take that reaction and flip it. So that's step 1 done. Step 2, I need to balance the electrons. So we'll do a little bit of simultaneous equations here. 2 and 3 both go into 6. So I'm just going to multiply this equation by 3, this one by 2, and rewrite them. Let's combine those equations. We can see therefore that those electrons cancel out. So there's our overall equation, and then our final step is to find the overall E theta of the cell, which remember I'm going to do by doing my most positive E theta value minus my most negative. So the most positive value was minus 0.26. Take away the most negative value. We've got 2 minuses in a row, which means we need to add. So our final answer here is plus 1.40 volts. In order to deduce the negative electrode, the positive electrode, and the direction of electron flow, let's have a look at this conventional representation. Remember that oxidation will always occur at the negative electrode because electrons will be lost. And so that is located here on the left-hand side of the salt bridge. Reduction always occurs at the positive electrode, so that's where electrons will be gained. So it's the nickel half cell over here. The electron movement is that it flows along the wire from the negative electrode, which we already said is the aluminium one, to the positive one, the nickel. In terms of any observations, be prepared to mention colour changes of the solution. What you'd find though is that the aluminium electrode would decrease in size because the solid aluminium is being converted to Al3 plus ions. That occurs because of oxidation occurring. Whereas over here, the nickel electrode would gain in size because we know that reduction is occurring, so we're forming more Ni solid. So just to remind you what we've done overall, we had a look at the E theta values in order to determine which reaction was reduction, which was oxidation. The oxidation reaction has the most positive E theta value. Remember that the reduction equation is written left to right. The oxidation reaction is reversed. We then balanced the electrons, we added the two equations together, we cancelled out the electrons to give us the overall equation, and then finally we calculated the E theta value by taking the more positive E theta value and then taking away the more negative E theta value from that to give an overall value of 1.4 volts. Remember, you could be asked to come up with the conventional representation of the cell. You'd be able to work that out through the fact that we've identified which equation is reduction, so we know that occurs on the right-hand side of the salt bridge. The left-hand side represents the oxidation reaction, and then the highest oxidation state species occur next to the salt bridge. Now, some half cells do not include metals, so some half cells do not contain a metal that can act as an electrode. In these cases, we use a platinum electrode, because platinum is unreactive and can conduct electricity, so it provides a conducting surface for electron transfer. So here's a good example of the Fe2+, Fe3+ half cell. We've got the presence of a platinum electrode. If we look at the conventional representation of the cell, because there's no phase boundary between the Fe2+ and Fe3+, look, they're both in the same solution, there's no need for a vertical line. We see instead a comma. Over here we've got the chlorine gas and the chloride ion half cell. You do have a phase boundary here because you can see the chlorine gas being introduced, the chloride ions in solution, hence the vertical line here. This represents the salt bridge, and remember that the species with the most positive oxidation number goes next to the salt bridge. This platinum here is the platinum electrode. Now, some electrochemical cells are set up using the same metal as the half cells, but with different concentrations of aqueous ions. So as is the case here, we have the Cu2+ present in solution, but 0.5 moles per decimeters cubed over here versus 1 mole per decimeter cubed over here. The first thing to be aware of is that the side with the higher concentration, so the right side here, is where reduction occurs. So I'll make a quick note of that here. So the side with the greater concentration of Cu2 plus experiences reduction, so that's why I'm adding 2 electrons here to produce that copper solid. So in terms of observations, you'd expect the solid copper electrode to increase in size, and the solution here will become lighter in colour as the Cu2 plus ions are used up. Therefore, it makes sense that the side with the lower concentration is where oxidation occurs. So let's write that equation for oxidation. So that's the loss of electrons. In terms of observations that take place over here, the solid copper electrode will decrease in size and the solution will become a more intense blue colour for the reason that more Cu2 plus ions have been produced and we've lost some of that copper solid. To set up an electrochemical cell, such as this one here, clean a piece of copper and a piece of zinc using fine sandpaper. This removes any oxide layer present on the metal. Degrease the metal pieces with cotton wool and propanone. The reason for that is that we need to remove the grease because it could prevent the cell from working efficiently. Place the copper in a 100 centimeters cubed beaker containing 50 centimeters cubed of 1 mole decimeter cubed copper sulfate solution. You may need to calculate the mass of an ionic solid containing the metal ions that would be required to make solution. And remember, we use moles equals concentration times volume to find the moles, and then mass equals moles times MR to calculate the mass of the metal compound required. Our next step is to place the zinc in a 100 centimeters cubed beaker containing 50 centimeters cubed of 1 mole per dm cubed zinc sulfate solution. Create a salt bridge using that potassium nitrate we mentioned before, which remember doesn't react with either solution. Connect the copper and zinc pieces using a wire and crocodile clips and include a voltmeter to determine the EMF. So now we're really going to apply what we've learnt. It does take practice, but we'll start here with question 1. We're using the electrochemical series below to select the species which is the most powerful reducing agent. So the first thing you need to be aware of is something which is a reducing agent is by definition oxidized, which means that it loses electrons. We need to look at the species on the right hand side. Let's look closely at the zinc because it needs to lose electrons in order to become Zn2+. So the species on the right hand side will be oxidized and therefore they'll be acting as reducing agents. The next thing to zoom in on is the most powerful one. Now the species which is most likely to be oxidized is the one with the lowest E theta value. This is something you have to remember. So as we look at the values, it means that it's therefore zinc. Select a species which in acidic solution will reduce this to this, but will not reduce this to this. So again, look at the table. We're looking first at row 6 because we're taking the VO2+, we're producing VO2+. So that we've been told is the reduction reaction, which means that has to read left to right. And it also means that it has to be the more positive of the E theta values when you compare the two equations. So that therefore means that we're looking at lower E theta values, but they've told us that it won't reduce VO2+ to V3+. So now we're looking at this row, so it can't be lower in terms of E theta values because it would allow this reduction. So we're looking for an equation that sits between the two. It's the one involving Fe3+. Because this is the reduction reaction reading left to right, oxidation must be occurring for this reaction, which means that the species that is being oxidized is Fe2+. Select a species which in acidic solution will oxidize VO2+ to VO2+. So let me clear up the table a little bit. So again, we're going from VO2+ to VO2+, so we're looking along this row. Because they're telling us that this is the oxidation reaction, we're going to be writing that equation back to front to show that this is being oxidized. It therefore needs to be the low of the E theta values. So now we need to find an E theta value which is higher, indicating that reduction is taking place. So that gives us only one option, this one with a high E theta value. It's got to be something which is being reduced, which is why it's the Cl2. The cell represented below was set up under standard conditions, deduce the standard electropotential for the following half equation. So they've given us the overall EMF, so now we need to find the E theta values for the oxidation and reduction reactions. Now, as you can see here, This is the reduction reaction. It makes sense. It's on the right-hand side of the salt bridge. So that's in effect our X value. Over here we have our oxidation reaction. So look in the table. We're looking along here. There's our E theta value. Now to find the overall E theta or EMF of the cell, we do E theta reduction minus E theta oxidation. We know the overall E theta of the cell at 0.48. The reduction value is what we're after. So what about the oxidation value? It's 0.77. So when you solve for X, you get an E theta reduction value of 1.25 volts. Write an equation for the spontaneous cell reaction. So we know that the E theta value is plus 0.48 volts, meaning that the reaction will be spontaneous. This is the reduction reaction. It's on the right-hand side of the salt bridge. This is the oxidation reaction. Just check the electrons happily. They cancel out. Now, because there's a 2E minus there and only 1E minus there, we need to multiply that one by 2. And then in terms of combining the equations, the reduction one reads left to right, so that remains the same. The oxidation one is reversed. And I'm just going to pop in the state symbols. Past paper practice. Table 4 shows some electrode half equations and their standard electrode potentials to deduce the oxidation state of nitrogen. Okay, so we know that oxygen is always -2. There's an overall negative charge. That means that if over here in total, because of that 3, we've got -6, it means the nitrogen here must be +5. And then here it's -2, so the nitrogen is +2. State the weakest reducing agent in table 4. So by definition, reducing agents are oxidized. We're looking for the most positive E theta value, looking down the right-hand side, because after all, these are the substances which will lose electrons. So the answer here is therefore the chloride ion. Write the conventional representation of the cell that has an EMF of plus 0.43 volts. So we're going to have to fiddle around with these numbers here to try and work out what combination will result in plus 0.43 volts. Remember what you're doing here to find the overall EMF, the E theta of the cell, is to pull out the most positive value and take away the most negative value. So it will take some practice to get used to what you're looking for here. I've written out the EMF equation. I'm just going to show you why it is 0.77. There's your most positive value, 0.34. You can see straight away how we arrive at plus 0.43. So then we need to identify which one's reduction and which one's oxidation. So remember, reduction is the most positive E theta value, oxidation is the lower of the two values. And so then when it comes to our conventional representation, we draw our salt bridge. We draw reduction to the right with the highest oxidation state closest to the salt bridge. If you check the state symbols, we can see that it's an aqueous solution, so that will be in the same phase, which is why we use a comma as opposed to a vertical line. There's our Fe2+, and then for the same reason, that means we have the presence of a platinum electrode. And then sort out the oxidation side, we have Cu2+ closest to the salt bridge. We have a phase boundary because of the solid versus aqueous. So there's our solid state symbol. Use data from table 4 to identify an acid that will oxidize copper. Explain your choice of acid. Use these data to suggest a possible equation for the reaction and calculate the EMF of the cell that has the same overall reaction. I'm just going to label this. So because the acid is causing the oxidation of copper, the acid is acting as an oxidizing agent, and therefore by definition it's reduced. So we can apply what we've learned to that electrochemical series. So if I have a look at the E theta values, I'm looking for a more positive E theta value. So that sends me up in this direction. Remember that an acid is a proton donor, so although you can't see HNO3 anywhere, it's fine because look, we've got the proton donor combining with the NO3 minus. Then it's important, obviously, that you pick the right species. Then, of course, because this is being reduced, you're allowed to write it left to right. So I'm just going to steal that equation as it is. Then we need the one with copper written the other way around because it's oxidation. Then we need to balance the electrons and then add them together, the two equations. Take your time here. And then finally, to find that overall EMF, let's do the most positive E theta value minus the most negative E theta value. So there's the most positive and there's the most negative. Right, lots of past paper practice here is key. So this question is about electrode potentials and electrochemical cells. State the meaning of the term electrochemical series. It's a list of electrode potentials in numerical order. The table below shows some electrode potentials. State two conditions needed for the following half cell to have an E theta value of 0 volts. So we're looking for our standard hydrogen electrode, which, remember, I taught you needs to have a temperature of 298 Kelvin or a concentration of hydrogen ions of 1 mole per dm cubed or pressure of 100 kPa. Identify the weakest reducing agent in the table. So reducing agents by definition are oxidized. So we're looking on the right hand side at the species which will lose electrons. The weakest one needs to have the highest E theta value because remember, the highest value refers to the species most likely to be reduced. So it's actually going to be this ion here. Use half equations from the table above to deduce an equation for the reduction of this to form this in aqueous solution by iron. So the first thing to be aware of is that we're carrying out a reduction reaction. So we need to look along this row in the table and the equation needs to read from left to right because that is reduction, the addition of electrons. And then we know that this is being carried out by iron. So by definition, the iron equation must be oxidized, which means it needs a lower E theta value. So the oxidation equation will be reading left to right, which means that it's the iron doing the reducing of this ion. Now, what's so insanely disgusting about this question is, yes, we know that oxidation will occur here to produce this ion, but the problem is that further oxidation will occur to this ion now because the E theta value here is lower than this reduction reaction here, which means that another reaction will take place to oxidize this complex ion to this one here. So that means that in order to oxidize both of these equations, you need 3 electrons, so you need to multiply this one by 3 before combining the equations. You're combining this one from left to right. Because this reaction occurs first, but it ends up with this product, you're actually going to combine this side and this side. Guys, please don't stress. This is the most disgusting question I've ever seen. So honestly, just move straight past it and it will not affect whether you get an A star or not or whatever grade you're after. Don't worry about it. I'm really running out of space here because then that one cancels out and this one becomes 3. So really you'd want to rewrite that again. Use data from the table above to explain why this complex ion will undergo a redox reaction with this. Give an equation for this reaction. Just get rid of this to make it a bit tidier. So we're looking at this ion. We know that because that has the most positive E theta value, by definition, that one's reduction. In terms of oxidation, when we look at these two, we know that it's undergoing reaction with this particular ion. So that ion needs to appear on the right with a lower E theta value. Yes, it has a lower E theta value, so that's okay. So that's where your oxidation will occur. So in terms of our explanation, we write that the E theta value of this reaction is greater than that of the Fe2 plus reaction. And then in terms of the equation, luckily the electrons cancel out. So you're going to write this one left to right and reverse that one. The diagram represents the cell used to measure the standard electrode potential for the Fe3+, Fe2+ electrode. Name the piece of apparatus labelled A. That's the salt bridge. What's the purpose of A? To allow ions to flow or to complete the circuit. Name the substance used as electrode B. Remember, that's your platinum electrode. It's inert. Complete table 1 to identify C, D and E from the diagram. Include the essential conditions for each. So C was your HCl. Remember, we want 1 mole per dm cubed. D is your hydrogen gas, which, because it's a gas, we need to state the pressure of it. It's 100 kPa. And then E is your solution containing the Fe2+ and Fe3+ ions. And we need a concentration of 1 mole per dm cubed. The standard electrode potential is plus 0.77 volts. Give the ionic equation for the overall reaction in the cell in the diagram above. State the change that needs to be made to the apparatus to allow the cell reaction to go to completion. Well, I know what that is. We need to remove the voltmeter. So in terms of that ionic equation, we know that the hydrogen gas is being oxidized. We know that the Fe3+ ions are being reduced. Then to cancel out the electrons, we need to multiply that equation by 2 and then add together the equations. The E theta values for 2 electrodes are shown. What is the EMF of the cell? So there's our salt bridge. This, remember, is reduction. This one's oxidation. Let's label them. So to find the E theta value, we do reduction minus oxidation. A student set up the cell shown in the diagram. The student recorded an initial voltage of this. Explain how the salt bridge provides an electrical connection between the 2 solutions because it has free ions. The standard electrode potential for the Cu2+ Cu electrode is this. Calculate the electrode potential of the left-hand electrode in the diagram. So in order to do that, we take the E theta value of the standard electrode potential and take away the initial voltage. Both electrodes contain a strip of copper metal in the solution of aqueous Cu2+ ions. State why the left-hand electrode does not have an electrode potential of 0.34 volts. The most likely reason for that is because the concentration is not 1 mole. Give the conventional representation for the cell in the diagram. Include all state symbols. So because this is an electrochemical cell using solutions of different concentrations but involving the same element, in this case copper, here's your lower concentration. Remember, that's where I said oxidation occurs. Your high concentration represents the reduction reaction. So we'll draw our salt bridge. We know that reduction's occurring, so we're going from Cu2+ to Cu. We put the highest oxidation state closest to the salt bridge. Make sure we include state symbols. Because it's going from aqueous solution to solid, we need a vertical line representing that phase boundary. And then the oxidation side, we're going to list that over here. Again, keeping the highest oxidation state closest to that salt bridge. When the voltmeter is replaced by a bulb, the EMF of the cell in the diagram decreases over time to 0 volts. Suggest how the concentration of copper-2 ions in the left-hand electrode changes when the bulb is alight. Give one reason why the EMF of the cell decreases to 0 volts. So if we look at the left-hand side, we know that oxidation is occurring there. Therefore, we're going to form more Cu2+ ions, so we'd expect the concentration to increase. And then reasons why the EMF decreases to 0 volts, because eventually over time the concentration of Cu2+ ions becomes equal across both solutions. The table shows some standard electropotential data. Use data from the table to deduce the species that is the best oxidizing agent. So it is being reduced, which means we need to look down this side, and we need the most positive E theta value, which we can see belongs to chlorine. A cell was made by connecting 2 half cells with a salt bridge. 1 half cell consisted of silver in a solution of silver nitrate. The other one consisted of tin in a solution of tin 2 nitrate. Calculate the EMF of the cell and write a half equation for the reaction that occurs at the negative electrode. So to find the E theta value, we're going to do the reduction value minus the oxidation one. And then what about the half equation that occurs at the negative electrode? So remember, at the negative electrode, oxidation occurs. So that's why we need the tin equation. Use data from the table above to write an equation for the reaction of silver 1 ions and iron 2 ions. So there's our silver ions. What about the iron 1? Well, if that's your silver, because compared with the 2 ions, it's more positive. It means that reduction's occurring, which means we need to look at the oxidation of both of these. So we're going to flip the equation, and it needs to be the one that's reacting with Fe2+. So it's only when you flip this one will it react with Fe2+. So that's oxidation. Handily, the electrons balance, so we can now combine those equations.